I knew the ribosome was important, but to be honest, many awards have gone to the ribosome, but not to me. And so I had gradually lowered my expectations of any such award. So I actually thought initially that it was a prank call. And because I have friends who do play this sort of prank, of course it would be a kind of cruel prank, but I nevertheless didn't really quite believe it. And I asked to actually speak to a member of the committee whom I know because he's a well-known ribosome scientist. And when I heard his voice, then it really sank in with a shock that it was real. So, well, I like to joke that ever since Rutherford, a knowledge of chemistry is not a prerequisite for this award, because I think I would flunk an undergraduate chemistry exam. So I'm kind of tickled to get a chemistry Nobel Prize. The ribosome is a large macromolecular machine. It's a molecular machine that consists of over 1 million atoms. Its role in all cells is to take the genetic information encoded in DNA, which is normally in the form of a double helix. Now, DNA gets copied to messenger RNA, and both DNA and RNA contain a sequence of the building blocks of nucleic acid, and that sequence specifies the sequence of amino acids that make up a protein. But to go from the language of nucleic acids, which has 4 types of building block, to the language of proteins, which has 20 types of amino acids, requires a translating machine. And that complex translating machine is the ribosome. And the reason that's so important is because many of the really catalytic activities of the cell and structures of the cell are made up of protein. By the time I started working on it, quite a lot was known. It was known that there were 2 subunits. The small subunit would bind this messenger RNA. The large subunit would form the peptide bond, that antibiotics targeted the ribosome. The problem was to go from there to a detailed understanding of the ribosome was very difficult. And that's because the ribosome is, as I told you, enormous. It's over 1 million atoms. And people made a number of valiant efforts over the years, which really vastly improved our understanding of the ribosome. But ultimately, I think a high-resolution structure it was clear that that would elevate our understanding to a new level. That's what allows you to know where the atoms are. And unless you know where the atoms are, you don't know where the bonds are, what's bonding with what the interactions are. And so you can't interpret things in chemical terms. And this is why I think the high-resolution structures really change everything. The idea of trying to get an atomic structure of the ribosome really goes back to Ada Yonath, who's one of the co-winners of this Nobel Prize. And she decided to try and crystallize the entire ribosome or ribosomal subunits. And initially her crystals weren't very good. There were a number of technical difficulties because no one had solved a structure nearly as big as a ribosome. It was a tremendous feeling because to actually see these proteins and large strands of RNA in the electron density meant we'd cracked the problem, and then it was a question of just improving the resolution to the point where we could actually interpret it in atomic terms. That was a thrilling period. If you think of these crystal structures, they're like snapshots of a particular state of the molecule. And as you know from looking at any machine like a car engine, machines move, they consume energy, they do all sorts of things. And so if you want to understand how the ribosome works, you need to get that snapshot at different stages of the process. And that's still an ongoing work in many different labs. And that's what we'd like. But of course, that sort of snapshot isn't really going to tell us everything or even much of the story either. I think the ultimate story will come from a combined effort from biochemists, geneticists, people who look at single molecule techniques. So all of these techniques are going to help unravel exactly how the ribosome works. That's going to take many years. But I think knowing what the fundamental architecture is in molecular terms makes all of this other work much more powerful. So I'm kind of dismayed to see this constant emphasis on translational research drowning out the idea that it's our basic research that provides the seed corn from which we can have translational research. Without these kinds of fundamental discoveries, and as I should tell you, the ribosome, right after the structures were determined, has already been started to be used for antibiotic design. But that's not why we did it, okay? And many discoveries like DNA sequencing, monoclonal antibodies, they're all billion-dollar industries now. And so, you know, you should have both, but there has to be the recognition that really fundamental research pays for itself many, many times over in terms of eventual discoveries and technology. And if you support that foundation, the rest will follow. I think you simply cannot do science in order to get a Nobel Prize. That's a route to failure and unhappiness. Okay, I think people should pursue science because they're interested in it. They should pick a problem that they love, that they care about, that they're dying to know the answer to. And then the prizes or the lack of prizes simply doesn't matter. If the Nobel Prize didn't exist, we would all still be very happy. In fact, we would be happier because of this limitation of 3 and excluding really important contributions. So we'd actually be happier in some sense if these prizes didn't exist and we pursued knowledge for its own sake.